Today we are looking at the SparkFun Circuit 2B of their Inventor's Kit. It is a digital trumpet. You can press one of these three buttons and a new note comes out. What I want to look at today is how the if statements are handled. Specifically, what happens if you want to program each of the combinations of buttons or groupings of buttons to do different things. So let's dive in by first looking at what they did. This is the diagram. They've hooked up three buttons, a little buzzer, and a potentiometer into the red board. Here we have it set up on my board, and when I press the buttons, the notes come out. But if you press two at a time, you just get whatever the last button was. There's no combinations. So that got me to thinking, why is it done this way? Looking back at SparkFun's code, you can see that the way that they're achieving their button is by setting up a series of if statements. But if you wanted to make other combinations, such as having two buttons at a time, you need to add another if statement. So in the end, how many if statements would you need to add to have each of the three buttons be independent and combined into different pitches? This is the formula that you may be familiar with that tells us the number of combinations of a set given a size of selection from the set. And when I look at this, it only tells part of the story, which is one particular size of set and one particular size of selection from that set. And a way to think about this is that in SparkFun case, they have given us three buttons, and they have also said you can only pick one button at a time. So the size of selection is 1, the total number of buttons is 3. So there's three options, button 1, button 2, or button 3. They've also given us the option to have 0 buttons pressed, and that's 1, because you can only have one way of not pressing any buttons. So there's really 4 options, and they've given us 4 if statements for that. Now, I wanted to see, well, how many combinations are there if you can press 2 buttons at a time? So if your size of selection is 2, K is 2, and N is 3, you plug it into this formula and you end up with 3, which is 1 and 2, 1 and 3, and 2 and 3. So then you can do the same with all 3 buttons at a time, and that's only one option. And then to figure out how many in total you have, or how many total if statements you need to have, you just sum them up and you get 8. So that's fine. 8 if statements is not crazy. Probably the reason that SparkFun only lets you do one button at a time is so that you wouldn't have to write out 8 different if statements, and you only had to write 4. But what if you have 4 buttons, and for each of the combinations you wanted to have a different tone? So then you can do the same math we just did, and you end up with 16 different combinations. And I don't know about you, but I don't want to write 16 different if statements. And even if I could, what if you want 5 buttons? Now there's 32 different combinations, and that's way too many if statements. And it could scale from there, because you can imagine that there's a lot of different ways in computer science to have many different options of things that can all act independently and all create different values when they're combined together. You can see that I've added a blue button to the SparkFun Inventor's Kit, and let's quickly go through the code that I'm using, because I made some slight changes to their code. First, I've created an array called note_r, which lists out all of the frequencies that I can choose from. And then I've created an unsigned car button byte, which is simply a bunch of zeros right now, and each 0 is a bit, and this B just tells the compiler it's a byte. I am starting up the program the same way, except that I've created a for statement here where it's assigning all of the different buttons without having to individually assign them, which doesn't really make that much of a difference between 3 and 4 buttons, but let's say I had 100 buttons. It would make a lot of difference. Then in my loop, what I'm doing here is every time the Arduino loops, which is many times per second, I'm creating a for statement, and each I represents one of the buttons. And just for convenience sake, I'm creating this variable readout, which tells me what Arduino is saying about that particular button. So that input that we're getting off of that button's port on the digital read. And then this is the magic line. This line here saves us from all of the if statements we could ever want. So whether we have 3 buttons, 4 buttons, 5 buttons, every combination possible, all the way to infinity, this one line will tell us which tone we should choose from the array. And then we've got this one line here which just makes the tone on buzzer pin 10 and looks inside node array for whatever the value of the byte is. This button byte is a byte. It's got all the different bits laid out, but when you put it inside this array, it gets converted to an integer in base 10 instead of base 2 with ones and zeros, and so very nicely will get us whatever note in our node array corresponds to the combination of the buttons we're pressing. So now we're going to take a look at this magic button byte formula. And all it's really doing is that for any number of buttons, we want to have it spit out at the end of it a byte that contains the last 4 bits that correspond to which buttons we have pressed. So in the case of having buttons 2 and 3 pressed, we want the right 4 bits of this button byte to say 0, 1, 1, 0. And if we had all of the buttons pressed, we'd want the right 4 bits of this button byte to say 1, 1, 1, 1. And then once we have that, we convert that into our base 10 value, which in this case is 6, and we take this 6 and we look it up inside our array. To do that, I want to go through this very slowly and imagine that this is one loop of the Arduino. And the Arduino loops hundreds of times per second, if not more. But we're just looking at this first loop. And what we're seeing here is what happens when we've just pressed buttons 2 and 3 at the same time. So right before we pressed it, our button byte was all zeros. It's how we defined it. And then as we move across this line, we see that not button byte is all ones. Our readout, which is what Arduino sends us, telling us whether the button is pressed or not, is all ones for button 1, because when nothing is pressed, Arduino sends true, all ones. And then what we're doing is we're taking all these ones and we're shifting it bitwise to the left by I. And what that means is we basically just add zeros to the right for how many places we want to bit shift it. In this case, I is 0, so we're not doing anything. Next, what we're looking at is not bit byte XORed to the readout shifted to the left by I. And in this case, it's all zeros because we're doing an XOR between not button byte and the readout shifted by I. And then we're taking this mask term, and you can think of a mask as a way for us to zone in on one particular button by setting its position to 1. So in this case, our mask for button 1 would be a 1 in the rightmost position with the rest of the bits set to 0. You could write that last term as 7 zeros and 1 as well if you wanted to. And we're shifting it to the left by I, which in this case is 0, so we're not changing it at all. Then what we're doing is taking a bit AND operator between the not button byte XOR to the readout shifted to the left by 0 and the mask. So we get 0 because 0 and a 0 with a bit AND gives you 0. A 0 and a 1 also gives you 0, because the only thing that will make a bit and operator true is when both of the values are 1. So then we're taking our zeros that we've just calculated, comparing it to our original button byte, and we get all zeros. So you can imagine that if we had no buttons pressed, all of these would be zeros. They would continue to run as zeros, and we would get a 0 at the end, which would be the 0 in base 10, which would then play the 0 element of our array. Luckily, we have buttons 2 and 3 pressed. So we take our button byte that we've just created from button 1, the I equals 0 part of the loop, and we loop it again. When we loop it again, button byte is 0, so it starts with where the button byte ended on the last loop, and then not button byte is all 1s. Our readout, which in this case, now that we've pressed the button, Arduino gives us false, so all 0s. So as long as we hold down that button, we will get 0s from Arduino. Then we shift all those 0s bitwise to the left by I, and now I is 1, but 0 shifted to the left by 1 with more 0s is still 0, so it doesn't do anything. And we'll see in button 4 why this becomes important. Then what we're doing is looking inside the parentheses and taking not button byte XORed to the readout that's been bit shifted to the left by 1, and we get all 1s. So we're comparing this button byte to our readout, and we're getting all 1s because each one of these bits is comparing a 1 and a 0, 1, 0, 1, 0. And so that means it's all true. It's all 1, 1, 1, 1, 1, 1, 1, 1, 1. Then we have our mask. So now our mask is the number 1, so 7 zeros and then a 1 in the 8th place. And we're shifting it by I, which is now 1. So we end up with this number, with a 1 second to the right. Now we're taking our bit AND operator, and we're comparing this mask, where the 1 is the 7th position, to all 1s, and we get all 0s because 1, 0 is 0, except for the second to the right. So now we have a 1, 1 here, and we end up with a 1. So if we compare this value that we've arrived at and XORed it with our original button byte from the beginning of the for loop, we get all 0s except for the position where we now have a 1 in the second to the right, and we have a 0 in the second to the right where we started. So we end up with this as our button byte. And this is what we wanted, because we wanted to say that the button 2, which is represented here by the second to the right bit, is 1. So now let's go to the for loop again, and I is equal to 2, and so now we're talking about button 3, and we start with a button byte that was the endpoint of our last loop. Then we take not that, so you see it's all 1s except for the 1 that we had up here, and then we take our readout, which again is all 0s because we have button 3 pressed. We shift it over by 2 now, but shifting it over by 2 just introduces more 0s on the right. Then we take our not button byte XORed with our readout shifted, and you can see that this would be all 1s except for the second to the right, which is a 0 in both the not button byte and the readout shifted. So we end up with all of the bits as 1 except for the second to the right, which is a 0. Now the mask becomes important, because what we don't want is all of our other bits to turn into 1, because that would tell us that our buttons were all pressed. So we have our mask of 1, and we shift it over to the left by I equals 2 this time. And so now if we take the bit AND between what we calculated here and our mask, we only get a 1 in this third from the right position. And that's what we want, because now when we take this element and we XOR it to our original button byte, we get 0s, so 0s and 0s are 0s in XOR. Now we have a 1 and a 0, so we have a 1, and then we have a 0 and a 1, so we have a 1, and then we have a 0, which we get a 0. So now we have exactly what we want, which is the buttons 2 and 3 represented by the second and third from the right bits in this byte. However, we still need to go through the for loop one more time for I equals 3, which is represented by this green button. So we start with our button byte that we ended with on the last loop. Then we take not button byte, which flips all the different zeros to ones and vice versa. Our readout now is all 1 because we're not pressing button 4. Then we shift over this readout by I. And this is where this shifting becomes important, because if we didn't do that, we'd have a lot of ones in here that would start to muck up and give us the wrong values for our other bits and represented buttons. So with our readout, bit shifted to the left by 3, now we can compare not button byte to the readout shifted, and we can see that the only one is that last one, because everything else is equivalent. So these ones match up, these zeros match up, but this is a 0 and this is a 1 in that rightmost term, so that's the only thing that is true, is that last bit. But that's not what we want, because that button is off. We don't want that one there. And luckily we have a mask here, and that mask is telling us that we only care about the fourth from the right digit. And that's exactly what we want. And so now we take this mask and we bit and operate on it for the value we calculated. And because nothing here is a 1 in both cases, we end up with all zeros, which is what we want, because a 0 compared with our original button byte will give us only the 2 buttons that we want to be ones, button 2 and 3, and then that last button 4 position has a 0 in button byte and a 0 in what we've calculated on the right in this equation, so we end up with 0 there as well. And that's how we get one loop. So you can imagine this repeating hundreds of times per second and having different values of all of our different buttons and our different combinations. We'll go through the same math, and then as you hold it down, all of these conditions will hold, and we have our number then that we can convert into base 10 that we can then put into our array to find out what tone to play. Phew. Well, that was a mouthful, but if you think about how powerful that one row is and how much it can do for you in terms of avoiding needless repetitions of if statements and expanding out into the realm of, let's say, 1 million different pixels that need to be individually adjusted by color, you can see how powerful it is, and it's worth the mental gymnastics to get there. And now, let's play for you our updated trumpet. And just for fun, I'm going to show you an output that tells us what on the left is the bit byte, what in the center is the corresponding base 10 value, and then what hertz it spits out. So if we press a 1 here, you can see that we've got the number 1, and then if we press the second button, we've got number 2. Third button would be in binary, combining that 2 with a 1. Then if we want a 4, we just press the third button alone. If we want a 5, we've got to add 1 to that. And if we want a 6, then we need to have a 2 and a 4. If we want a 7, we hold down all 3. And we've even got all 11s and turning it up. So, in a sense, we've taken this digital trumpet and turned it into an auditory counting tool for learning binary math and making weird bagpipe noises. If you've enjoyed this video, subscribe, click all the buttons, let me know what you think. Thanks for watching.